Okay, so first let's have a review of the formulas that we have learned last time. So it's 7.1. We learned this integration. So we will use IBP for short. Integration by parts. It comes from a formula we learned before, the product rule. FG. Okay. For this, we apply the fundamental theorem of calculus. We get that the FG in particular, if we want to find this integral, it can be represented as f and g, they're functions. We don't need to do anything about them. Here we have two integrals. Our expectation or our purpose is to make this one simpler than this one. In this case, the integral of this more complicated function reduce the integral of a slightly simpler one. Okay, so that's the phase, and we had quite a few examples. Okay. Again, we want to make the integral simpler. So the criteria is f derivative is simpler. And the g is not more complex. Okay. So sometimes if you try this in the first, you go to the wrong direction, then you make changes. You go to the other direction. We want the integral to become simpler. This one, we identify this as f, the g derivative. So we can verify our criteria. The derivative is simpler than f, and g is not more complicated than this one. This gives us the correct direction. So we can go with the formula. F derivative. So copy the formula. F G X 1. Okay, so that's the idea of integration by parts. We want to make the integrand simpler. Sometimes we have to do this more than once. Another example. This one, we apply the integration by part once. this will be our f, our g derivative. Again, we have the same criteria. We check the derivative of f is 2x is simpler than x squared. The antiderivative of this is e to the x, not more complicated. Okay, so f g. Plug in the terms. F is x squared. It's x to x. So we have to do this one more time. One more time because we have done it already. So we can use what we have done and copy the result. We build on this twice of the first step. Again, an integration constant. Okay, any question about this too? Okay, all good. Then let's go one step further. X cubed e to the x dx. Okay, I will give a minute to figure out what would you do for this one. Sophia and Elisa, questions? If no, let's get the work started. Okay, yes.
F prime is going to be 1/4. Wait. It's going to be 3x squared.
Okay, so this time, again, I will copy the formula. F is x cubed g to the x, derivative 3x squared. So x cubed e to the x 3. Again, we check what we have accomplished in the previous step. We found that the integral of x squared e to the x is this. We subtract 3 times of it. Again, an integral constant, not distribute. Okay, so this step by step, we can find all integrals of the polynomial with e to the x. You can replace this by cosine x. You can find x cosine x, x squared cosine x, x cubed cosine x. Similarly, tangent x, you can do this one by one. Next, okay, the very important one is this. Okay, let me check. Sakina, do you remember how we integrate this one? Let's try to recall your memory. Okay, you were not here. Do you watch the videos? Okay, so what have we done for this one? Uh-huh. Okay, Sophia, do you remember this one?
You do ln x times 1.
Okay, so here we supply the 1 over there. Let's make a different color. 1 dx. Okay, so now we can, this will be our f, this will be the g derivative. F derivative is 1 over x. So this is much simpler than this one. Even though g, we get some complexity for g, but compared to the gain, we still make it simpler. Okay. Because this is much simpler than logarithm. Even we lost something in this direction, still have some benefits. Okay, so this is f g f is logarithm x, g is x. F derivative 1 over x, x dx. Okay. The overall of the integral from here to here, one becomes much simpler. The other one slightly more complicated. So it's a way we find the integral. Okay, very useful approach. Then we start the next section about the trigonometric functions. How do we integrate trigonometric functions? The first part is this cosine nx polynomial of cosine and sine. To integrate this, we divide it into several cases. The first case, when let's see, n is even, odd, n is 2k plus 1 plus odd. If one of the index is odd, if let's say this one is odd, then we can split and have one more cosine x dx. If one of the power is odd, we split this to 2k and 1. Then we use the substitution. So this will be our substitution. The substitution, the derivative, and the differential form. So cosine x dx, this becomes du. U is sine x. This will be u to the m. What about this? How could we convert this cosine to kx to a function of u? Okay, think about this. Let me write the remaining terms. The chain. We wanted to write this as a function of u, something gu. So Kina, you want to try? Okay. Okay. And Sophia. Cosine square x. Does this ring a bell or something? How do you?
Oh yeah, cosine 1 minus cosine square x. 1 minus sine square x. Oh.
Okay. Now if I take in our case, u is sine x. So I can continue from there. Then, okay, so Chen, how do I get 2k power from here? From square to 2k, how do I do that? You take the whole thing, power k, you take the whole thing, power k. Now we convert this to a function of u. Can you see the difference? We started with a trigonometric integral. In the case when one index is odd, we use the substitution that converted to a polynomial. We know how to integrate a polynomial. It's one of the easiest class of functions. We integrate this, then we switch back to x. Okay, let's try the second case. First case, second case, when m is 2k plus 1 is odd. What should we do in this case? Okay, I will give you a few minutes to figure this out. Cosine nx sine 2k plus 1. How do you integrate this trig function? Any clue? Any ideas? Okay, Sophia, you want to say something?
Substitution,
Okay, so what's your u?
cosine x.
Okay, what's the derivative?
Negative sine x.
Okay, what's the differential?
Negative sine x dx.
All right. Okay, so now we will split cosine x. So just one more step. Sine 2kx sine x dx. In this case, we have u to the n, and that with negative du. Sakina, how should we deal with this term? I wanted to write a function of u. Okay, yes, exactly the same. Very nice. 1 minus u squared k. Again, using this substitution, we convert this trig integral to the integral of a polynomial. And this is easier to integrate. After integration, we switch back to x. We have what we want. Okay, so first case, this is odd. Second case, this is odd. What's the remaining case? Okay, okay. What's that? Okay, I will let you file it down. Okay. Okay, Sophia, what's the remaining case?
None of them are odd. Or all of them are odd.
Okay, so first case, this is odd. Second case, this is odd. what's left is none of them is odd. So both must be even. That's the remaining case. Both M and N are even. Okay, so let's introduce the even numbers. M equals to K, N equals to L. So our integral is cosine to Lx sine to. Okay. This time we cannot use a substitution. We're not ready yet. So what we do is we use this double angle formula to reduce the degree. The double angle formula. Cosine square x Yeah, that's a very tiny difference. Okay, very good in the notice. So for cosine, it's 1 plus. Sine is 1 minus. Okay. Now we use substitute. Okay. So which word? Did I say something? No? Okay. Okay. So sometimes if I say something funny, you can correct me. Okay. Okay. So this will be. I know. I understand. I have been there before. Okay. It's okay. 2x. Okay. Now what's the power? Okay. Very quick. So not bad. 1 minus cosine 2x. That's then what's the power? K dx. Okay. Now let's see. After this one step, we reduce the power from 2L to L, 2K to K. So we reduce the power. Then it's get more complicated. That's for sure. Have a lot of terms, but each term comes with lower degrees. And then we can go back to check. Are we ready to apply the substitution, or do we need to apply this rule again and again? Okay, so case by case. So for this trig function, trig integrals, the second class we started last time, but we didn't finish. It's very similar. Tangent mx secant nx dx. Okay, let's give a brief review of the first three functions we did last time. Okay, Sakina, how do we integrate this? Tangent. Okay, let me think about that. Maybe it works. Maybe we have a simpler way. Simpler way is we use the definition of how do we define tangent x? Sine over cosine x. Okay, now we want to use substitution to make this simpler. U equals cosine x. Okay, let's think about this. How do we do this substitution? So denominator, that's the simplest one, just u. How do we deal with this? We need to figure out what's the du, Zichen. So this is u. What's the differential? Maybe what's the derivative? Okay. Yes, okay, so that's perfect. So we can skip the derivative, we go straight forward to differential. Okay, so here we have sine x dx. We're missing the negative sign. We'll put a negative sign over there. It will be negative du over u. Okay, Sophia, how do you integrate this integral? d1 over u du. And the 2 of u, how do you integrate this? And to make this more general, because u may be negative, so I will put an absolute value over there. Let's recall, if we take the absolute value, take the derivative, we recover this. And in the end, we switch back to a function of x. U is cosine x. Okay, that's the first one. Second one, let's raise the power. Tangent square x dx. Okay. This one, we know that the derivative of tangent is secant square. This, what's the difference between tangent square and secant square, Zishan? How do I go from tangent to secant square? Ask
Minus
Skinner.
1.
Okay, yes, Sophia knows. Okay. So we know that secant square is 1 plus tangent square. So secant square is 1 plus tangent square. We only have tangent square here. How do I get secant square? We have to add 1, then minus 1. So this gives the square, minus 1 stays. This will be minus 1. Does it make sense? Plus 1 went inside. Right? Okay. Tangent square, we add 1. This goes to there. Subtract 1 because we want them to be equal. Okay. So the integral of the difference will be the difference of the integrals. So now this will be tangent square x. Oh no, tangent x. Okay. Integral of the cube. So for this one, again, we will split the degree. Split it to a square. For the square term, we use the same trick. Secant square is 1 tangent x. Then we distribute. The integral of the difference will be the difference of the integrals. Okay, now we can say from sec tangent cube to this integral, this integral. Let's focus on the first one. How do we integrate this? We have this secant square and I have tangent. If we want u substitution, what would be your u? Okay, so we have one candidate. For the first one, we set u equals tangent. Okay, what's the du? It's correct. It's correct. Derivative of tangent. Okay, so we use the substitution. Okay, now tangent is equal to u, secant dx goes to du. And for the second part, we have done it over there. So I'm going to copy the function. Okay, so this integral is easy. 1/2 u squared plus sin x integral constant. Then we switch back to x. 1/2 tangent squared. So it's the integral constant, not x. Mistake, correction. Okay, a little bit more work to find the integral of the cubic power. Okay, the next one, we will move to secant. Have more enough space. Okay, how do we integrate this one? Not easy, okay, just one, but where do we start? Okay, very good, let's try that. So by definition, secant is 1/cosine. Okay, we want to use substitution. What substitution should we make? If u equals cosine, then du will be negative sine x dx. Denominator, okay. But the numerator, we only have dx. We are missing this term. It's not there. So this substitution will not make it simpler. Okay, that's our first attempt. Do not erase, do not erase. You can just say. So that's our thought process. How do we integrate this? Okay, so this one not work. One way is we can make up a factor we need. I'm going to multiply this by cosine, cosine. Denominator will be cosine squared. You can see how we deal with that. 1/cosine x. Okay, that's first attempt. Second attempt. Mr. Chen, now it's your turn. What substitution would you make if we integrate this one? We have cosine x dx. Okay, something with a derivative is cosine. Let's try if we want to make this work. Okay, what's the du? Cosine x dx. Okay, this time we are done with the numerator. What's the denominator? Could we represent this as a function of u? Okay, nice. Okay, a substantial progress. Another difficulty. How do we integrate this? Do we have a formula for it? Okay, now you should refresh your memory going through the list of derivatives integrals. You have we seen anything like this before?
And
Sophia, what do you think?
it's like
If. Okay, that's the if. If it's plus, what do we have? If it's plus, it will be arctangent. However, we only have minus. This one is kind of complicated. We're not ready to integrate it directly yet. We'll do this maybe after one more class. A new method called integration by partial fractions. Okay, so we will come back to solve this. This is a very good progress, but we're not ready to complete it yet now. So come back to later. Okay, so this is our thought process. Give us a new integral. Sometimes it's not very easy to integrate. We try this, it doesn't work. We try something else. We want to make it simpler. See when it works. Okay, that's a different approach. A different approach, we want to multiply, retry. Okay. So I multiply secant over secant, so it's the same integral, secant squared dx. Okay, Sophia, if you see this integral, what substitution would you pick?
and
Tangent. Okay, so this one we would see. I'm going to use d tangent. Again, we get stuck. If we have tangent on the denominator, then we know it's the logarithm. However, we have a mismatch. Tangent secant. Okay, let's pause and try a different. Secant x. Let's try tangent, see what we get. Secant x tangent x dx over tangent x. Okay, the two of you. Substitution. What substitution would you use for this numerator? D something. Whose derivative is secant x tangent x? If secant square is the derivative of tangent. Okay, let me refresh this. So this will be the derivative of secant. Okay, try to check it. If you recall this, this will be the derivative of secant. Again, we have a mismatch. Over there, we have secant. If we have secant on the denominator, then we know how to integrate. We use u substitution, du over u, it will be logarithm. However, it's a mismatch. We cannot do that. However, let's check these two methods. This is d tangent over secant. This is d secant over tangent. I have a match over there, a match over there. So to integrate this, we will combine these two approaches to get a match between tangent and tangent, secant and secant. Okay, so that's the idea. Okay, so now we are going to combine the two approaches. Okay, I'm going to multiply the combination. So sec x tangent x tangent x secant x. Okay, first to confirm they are the same integral because the numerator and denominator are the same. Secant square x secant x tangent x. Okay, now let's think about this. What substitution should we use? This time, this whole thing will be our u. Okay, u is tangent x. Okay, Sophia, what's du?
It's secant squared x plus secant x tan x.
This is exactly we see we made up over there. So we can rewrite this using this substitution. Du over u. Okay, now how do we integrate this? Sakina. Du over u. Zhichen, maybe rewrite 1 over u du. Is helpful? Uh-huh. Okay, again, absolute value. Then we switch back to x. So tangent x, secant x. Okay, so you can see this very simple integral, secant, we have several attempts before we come up with a non-trivial substitution to get the integral. We tried this substitution, it didn't work. We make a manipulation, we get something, make some progress, but we couldn't finish. Then we try this, get a mismatch, try this, another mismatch, but the two mismatches give us a match. Then we use a substitution, we get the integral, switch back to x. Okay, so the formula, secant x dx. The next one is easy, secant square dx. Okay, who can give me the answer? Okay, nice. This is much easier. Okay, we will have 5 minutes break, and after the break, we will do secant cube x. Okay, 5 minutes break. Okay, we're back to this one. In this one, we learn a new method, approach that sometimes we don't get, we want to simplify the integral. Sometimes we failed, we cannot simplify it. We get something with the exact same complexity, and we will utilize that. Okay, so again, the cube, let's split this to secant and secant square. Okay, so then when you substitution, this will be f g derivative, integration by parts. Okay, Zichen, what's it? G? 10. So it will be f g minus f derivative g dx. Okay, so f is secant tangent. Okay, Sakina, g derivative. I'm sorry, f derivative. Secant derivative. Secant and tangent. A little bit rare. Okay, this is so the derivative will be secant x tangent x. And we copy function g tangent x dx. Okay, one step, integrating by parts. Okay, now let's rewrite. Okay, let me continue from there, have more space. Secant x tangent x, secant x tangent square x dx. Okay, have a tangent square. How do we deal with tangent square? Okay, Sophia, how do we deal with tangent square? What are the approaches for this?
You make it 1 minus secant
Uh-huh,
square.
okay. Secant x tangent x, secant x, secant. Then the integral of the difference of the integrals. Secant x tangent x, secant cube x minus minus plus. Okay, interesting thing. We wanted to integrate this. We do quite a few steps. We end up with something with a exact same term with opposite sign. So here, we cannot go further without thinking, where should we go from here? We didn't simplify even a bit of it, because they are exactly the same. It's not simpler. It's not simpler, but the good thing is it's exactly the same. So we can treat this as an equation of this. We try to group these two together. So how do I group them together, Zichen? Easy. Do not overthink it. These two. We have an equation. On one side, we have one term. The other side, we subtract the same term. How do I simplify it? 2 times. Nice. Okay, so instead of completing the integral, we treat this as an equation. So twice of it will be this with this. That's a very big progress. Twice of the integral. So instead of the integral, we solve the equation. This secant cube will be half of secant x tangent x, half of this integral. And we have done this in the first step. I'm going to copy the result. Secant is this. I'm going to copy it, the result. Solving the equation gave us the integral. So a new method. We wanted to simplify it. We didn't success in that direction. However, this process create an equation about this. We can solve it from the equation, we get the integral. Okay, so you have something like this in the homework. You try this integration by parts, you do it again, you get exactly the same thing where you start. You realize, okay, that's an equation. We can solve the equation to get that integral. The new method, get an equation about the integral. Okay, so these are the special cases. Now with this preparation, we can try the general formula. Tangent mx secant nx dx. Okay, let's look at the results we have done before and see which are the easy case. For secant, you have all the power, not easy. All the power, not easy. For secant, you have even power. That's the easiest case. Okay. So the first case is even. And even we can split a square. Tangent mx secant minus 2x secant square x dx. Okay. We split the two out. Then we have the substitution. Okay, Zichen, what's the substitution for this one? So that works. Okay, not what, it works. Okay. Okay, so now, so this will be our du tangent um. Okay. Because n is even, let's say n equals 2k plus 2. Then I will switch this by just 2k. Okay, Sakina, how do you convert secant 2kx to a function of u? Okay. Okay, yes. Now you know where this goes. U square plus 1 to the k. Again, for this trig integrals, if we can convert it to integral of polynomials, we will call it a success, because this we can always integrate it very quickly. Whenever we convert it to a polynomial, we say, okay, that can be done. second case. Second case when m is odd. M is odd, so we use m equals to k plus 1 tangent to k plus 1 x secant n x dx. I'm going to split. I'm going to take 1 degree from there, another degree from there. I take one of them, tangent x secant x dx. What's left will be tangent to kx secant n minus 1x. Okay, now we use a substitution. So u is secant x. The whole thing becomes du. So this will be u n minus 1. Zichen, how do you deal with this? Could we convert this to a function of u? U is secant x. What's tangent square? Tangent square is secant square minus 1, right? Okay, and we know u is secant. This will be u square minus 1. We can convert this to a function of u. So whenever we convert a trig integral to a polynomial, we call it a success because we can integrate it. Okay. Okay, so we have done 2 cases when n is even or when m is odd. What's the remaining case? Okay, Sophia, what all integers. Now we deal with even n. We also know when this is odd, what's the remaining case?
They're both even.
Not okay, so this is slightly different. If n is even, whenever n is even, we use this substitution, we convert it, we know how to integrate. Whenever m is odd, we know how to integrate. Okay, now what's the remaining case?
N is odd.
N is odd
And
and
M is
m is
even.
even. Okay, the remaining case, n is odd, m is even. None of the substitution works. So in this case, you have to use this trig identity to convert it. So trig identities. Okay. So this is about the trig integral. We have done a few, and the general case can be done separately. So we will move to the next section. Closely related. So we know how to integrate the trig functions. The trick is to convert the polynomial. Now we will want to utilize what we have learned with trig substitution. So in many cases, we have a very complicated integral, but we can use the trig substitution to convert it to a trig integral. Then we use the method we learned before to do the integral. So general trig sub, they become trig integral. Then 10.2, we know how to do this. So we from the trig integral go one step further, come even more general ones. So there are special types of integrals that will benefit from this trig substitution. The first one is if we have a factor if our integrand has a factor like this, Sakina and Suchen, has a factor like this, is the square root of 1 minus x squared. Whenever you see the square root of this, it's a hint that we want to apply the trig substitution. So because we want to get rid of the square root. Whenever you see this, you see first thing how to get rid of square root. We use the trig substitution. First the domain, so x equals sine x theta. For x varied from -1 to 1, what's the domain for theta? Sophia?
It's
So here we can pick the interval have two on this interval. This is a one-to-one function. The square root. Okay, so Chen, if x is the sine theta, what is the square root of this? Okay, steps, not the result. Okay, steps. Y minus sine square. How do you simplify this? Y minus sine square. Okay. What's the square root of a square? Okay, could be yes. So absolute value of cosine. Okay, the interesting thing in this setting is on this interval. What's the value of cosine on this interval? Negative pi over 2 to pi over 2. Could be negative. Cosine function, if you see the graph, negative pi over 2 to pi over 2. So on this interval, this function is non-negative. So the absolute value of a non-negative number is the number itself. So this is very important step because cosine theta non-trivial. Okay, now let's do the integral. Let's start with this one. 1 over without the trig substitution. How do you do this? Okay, let's try the substitution. Let's try the substitution. X equals sine theta. What's the denominator? Cosine theta. Okay, the difficult part. What's the dx? Sophia, what's the dx? X is sine theta.
Negative. No, just regular cosine x.
Be cosine theta d theta. Okay, so this is dx, so dx, the differential, d theta, I'm sorry, not the dx. Now we have the cancellation. This is the integral of 1 d theta. Okay, so can I what's the integral? Yes, but now we are using this theta variable. So it will be theta plus c. Okay, how do we go from theta to x? We want to get a function of x, something x plus c. So check. X is a sine theta. So what is theta? Inverse function. The inverse function. Does this ring a bell to you? The integral is the inverse. Okay, let's recall in chapter 3, we learned that what the derivative of this is this. Okay, recall we learned before.
Isn't it 1 over square root of 1 minus x squared?
Mm-hmm. Okay, now let's try to refresh our memory. How did we find this derivative? What method we use?
Implicit.
Okay, I have one response. Sakina, what method we use to find this derivative of the inverse function? Ask Zishen, she knows. So this is the implicit differentiation. Oh, right. Oh, yes. Okay. So the ring some bells. That's good thing to know. Implicit differentiation. Okay. Now a similar one. Let's find the integral. Okay. I'll give you a few minutes to try this one out. How do you integrate this? Where do we start? Yeah, you can chat. You can ask each other. What do you think? Substitute what? Okay. So whenever we see the factor like this, square root of 1 minus x squared, we use this substitution. So we substitute x by sine x. Then what's this? Cosine, nice. Okay, this will be, again, what's dx? derivative, cosine. How do we integrate the cosine square? Cosine square. So we want to reduce the degree. How do we reduce the degree? Square. The double angle formula, what's that? Double angle formula for cosine square. Then we integrate. Again, I get more space. It will be theta. Integral of this one. What's the integral of cosine 2 theta? Think about it. If it's cosine theta, what's the integral? Sine. Okay, now I have cosine 2 theta. It will be sine 2 theta, but with some correction. What's the coefficient?
1/2.
Nice. Nice. Okay, so the result is, okay, again, we want to go back to x. Go back to x. So sine theta, we have done this before. Sine x 1/2. For this one, to get back to x, we use a double angle formula. So 1/2 it will be 1/2 to sine theta cosine theta plus c. Sine theta is x. Cosine theta, as we have done before, is a square root. Okay, let's go back to. Okay, so the final result will be 1/2. And 1/2. Okay, very complicated integral. And this is made possible using this trig substitution. Whenever you see a square root of this, something like this, use a substitution. And a slightly more general case. If we have sine, we use a substitution. Now if we have 4x squared, what substitution should we pick? Similar, but need some modification. The purpose of this substitution is to get rid of the square root. So here we pick this, we get cosine square. So we can get rid of the square root. How do we get rid of the square root? What substitution should we pick? Could we use the same substitution, sine theta? That work? No, because there was 4 minus sine square, we cannot get rid of the square root. What should we do? Okay, we want to get this 4 sine theta square. If we take a square root, 2 sine theta. The purpose of this is to get rid of the square root. This implies, what does this give us? Let's simplify. Pick up the 4 of square root of 4. This gives us 2 cosine theta. Again, we get rid of the square root. Okay, now a general case, if a positive number a, we want to integrate a squared minus x squared dx. What substitution should we pick? Sophia, what would you pick?
Mm,
If it's 4, oops, we pick 2. Now have a squared. What do we pick?
A.
A, yes. Okay, have a few minutes, we can finish this. A sine theta. What's the square root of this? It's Sakina. It'd be a square sine theta square. So we take a square root, it will be square a, because a is positive. A Again, this help us get rid of the square root, because the square root is a troublemaker. Okay, and again, a positive. 1 minus a squared x squared dx. What substitution do we pick? Do we use the same one or do we use a different one? A squared here, a squared there. Okay, nice. You know how to adjust it. It will be 1 over a squared, a sine theta. The reason for this is we want to get rid of the square root. That's the main purpose. 1 minus a squared x squared. Okay, we simplify this. Okay, Zishen, you give us the idea. How do you simplify this? How do you simplify this? Okay. So these are the cases. How do we integrate a square root factor with the difference of two squares? We use this trig substitution. It will help us to get rid of the square root. Then we integrate the trig integral, and we know how to integrate that. Okay, so we will stop here for today's class, and next time have more trig substitutions. So this chapter is not easy, but it's the main part of the calculus. How do you take derivative? That's easy. You just follow the steps. but integral have to try. If it works, okay. If it doesn't work, a different method. Okay. Okay. See you next time. And Sophia, questions?
No.
All right. Okay. Next time, Elisa.